let's move over from finding the joint density function of random variables to how to quantify or characterize these random variables through numbers or etc. So this we have done for one random variable. If you recall, a random variable of course has its density function, but then we also defined characterized it through its moments, right? Remember, mean is an average value, then variance, which gave you a measure of dispersion, and other higher order moments, etc. So here the natural extension would be, if you have a function of x and y, how do you define, or let me say, you define a function z to be g of xy, and of course on this side you have the joint density function of x and y. This is given. And this side, if you want, we can go through these techniques and you can also compute the density function of z. So of course here, if you have a random variable z, its expected value makes sense. So the expected value is, as we have seen, it is z fz dz. But on the other hand, since z is given to be a g of x comma y, we also know that expected value of this function is actually equal to this, right? Because everything is equality here. But if you go this way, what is the trouble? The trouble is no trouble, except you do need to compute this function. This is generally not given. And you have seen the computing, this is not like substituting something. It is not trivial, it needs some work. So you should compute it if you have to compute it. But it's you can think that since this is an average value, expectation is an average value of this function of two random variables, it is conceivable that this quantity, remember after all this is a number, this is not a density function, this is a number like mu z, right? So you have two ways of expressing, you can express it this way or this way, both are equal. So this number could be expressed in terms of the density function of z, or it also could be expressed in terms of the joint density function of x and y. So the argument is exactly the same, very similar to what we had in the one random variable case. So if you take a point z and you have a small variation z to so you have z here, c corresponds to some gxy in the xy plane. So you have a probability of random variable z being between z and z plus delta z is fcc dz, and this also corresponding, depending on this, you can write in terms of fxy xi comma yi dxi dy, and then when you multiply this side with z, here you multiply this with gxy, and then you here sum over all values of c, and here also you sum over all values of c, and these solutions are going to be non-overlapping. Consequently, this integral will turn out to be a double integral over the xy plane. So this we can write it as gxy fxy dx dy. So in particular, if they remember, if this is just a function of x, we already had this formula. Expected value of gx is gx multiplied by fxx dx, right? You don't have to find the density function of gx to find the average value. So this opens up all sorts of possibilities. So for example, so from here You can take any function of x and y, as in the before we could define the generalized moments, for example. Okay. So this is going to be double integral xm yn fxy x comma y dx dy. One important thing I want to say, so this is in general. Suppose gxy is of the form h1x multiplied by h2y. Here it is separable functions. So in this case, this will become double integral h1x multiplied by h2y multiplied by fxy x comma y dx dy, right? Hello? Can I, of course, one integration is on x, one is on y. In general, it's like this. How do I, can I write this as the product of two integrals? When? Look at here, this. Only if they are independent, very good. So suppose x and y are also independent, then you see this becomes, of course, fxx multiplied by fyy. That may or may not be true. You have to look at the problem. If it is true, then this becomes h1x multiplied by fxx dx multiplied by h2y fyy dy. But this, as you know, is expected value of gx, right, or h1x multiplied by expected value of h2y. So what is, this is a theorem. What is the theorem? If x and y are independent, so this qualifies as a result. If x, y are independent, then expected value of gx multiplied by hy is the same as expected value of what? Anyone? We just wrote it here. So this is h1, this is h2. You need independence here, then this is true. So look here, if x and y are independent, this can be written as what? So because this is gx, this is hy. So expected value of this multiplied by expected value of this. But they need to be independent. It may be independent, may not be independent. Okay. So this, let's keep this in mind. So what happens, I would ask you this, what happens to expected value of xy, because this is the simplest moment you can think of under this condition. If x and y are independent, expected value of xy is multiplied by expected value of y, but that's the mean of x multiplied by mean of y. Expected value of x squared multiplied by y squared would be x squared multiplied by expected value of y squared, etc. Okay. So we had defined variance to be what? Expected value of x minus, anybody remembers? X minus mu x the whole squared, right? The actual observation minus its mean, this is the error, square, the mean squared error of the. So this, if you remember, we could also write this like this, right? And this is always positive because this is a quantity multiplied by the density function, but the quantity is positive, right? Similarly, you had sigma y squared to be expected value of y minus mu y the whole squared, right? So this is expected value of also positive. So look here, how many parameters you see here? I see two means, I see two variances. But what are the problems with these parameters? The mu x and sigma x only deals with, you only need the density function of x to find out, right? Because this is x minus mu x, the whole squared fxx dx, right? Similarly, this is y minus mu y, the whole squared fyy dy. What is my point? So far we haven't used the joint density function anywhere. So I'm going to bring in the joint density function. So the simplest way, if you want a parameter, remember I have four parameters, the mean and the two variances, but they don't tell me anything about their joint behavior. So the simplest way I can bring it in here is put m equal to 1, n equal to 1. So expected value of xy is of course a double integral xy fxy x comma y dx dy. So I am going to create a new function from here. Anybody, what do you read this as? Put x equal to y, what do you get? Look at here. You put x equal to y, what does this become? X minus mu x multiplied by? So what is that? That's the same as this, isn't it? So this is the variance. So this is the covariance. COV stands for covariance because this is, look at here, these are the variances of, this is the variance of x, this is the variance of y. So here in this notation, if I put x equal to y, now this is simple algebra. Let's expand this. How many terms are there? 4 terms, right? Look at here. What are the terms inside? Expected value of x multiplied by y minus x multiplied by mu y minus mu x multiplied by y plus mu x mu y. But you know, expectation is a linear operation which you can see from here if you have additional functions. So this is true, right? So linear operation, I will write it here. So expected value of sigma g I xy I equal to 1 through n is same as, so this thing multiplied by double integral summation gi xy multiplied by the joint density function of x comma y dx dy. But I can take the summation outside. Yeah, let me also put an ai here, constants, it doesn't matter. So I pull out all the constants outside. Then it becomes expected value of gi x comma y. Because the remaining term is gi double integral gi fxy, that's the expected value of this. So expected value of this is the sum of the expected values. Look at this. So the first term is expected value of xy. What is the second term? This is a constant. Constant multiplied by expected value of x is? So the first term is expected value of xy. Second term is mu x mu y, and this term mu x mu y, and this is plus mu x mu y. So you get this to be the answer, isn't it? Because this and this will cancel, or this and this will cancel, and you get this one. So it all checks out. Put x equal to y, you get expected value of x squared minus mu x squared, like very similar to this. Okay. So if you have this, let me write it down here. So I have covariance of x comma y is defined as expected value of x minus mu x multiplied by y minus mu y. So if you want, or you can also write this as xy minus mu x mu y. Okay, very good. So that's covariance. Covariance will be positive or negative. Anybody? In general, you cannot say because I don't see here. Of course, why is this always positive? Anybody can give me the reason? Why is the variance positive? Yes. Because look, some function. Function is already positive multiplied by the density function, always positive. So if you integrate a positive function, you get a positive number. Here, this function could be negative. This is depending on, there is no square here, right? So this could be negative or positive. Now look at here. This is you can show that maybe this is what the covariance is going to be less than, this function is less than or equal to sigma x, sigma y. So let me show you that first. So let me show you why that is true. What is the mean of this random variable z? Anybody? What is the mean of this random variable? Is the mean on the right side? Expectation is sum of the expectations. So what is the expectation of this term plus expectation on this term? Anyone? Okay, what is the expectation of this term? What is the expected value of this? Minus expected value of constant, which is constant itself. So mu x minus mu x. What is the expected value of this term? So that's so if you subtract the mean, you of course you get a random variable with the zero mean. So what is the variance of z by definition? Expected value of variance of z is what? Expected value of z squared, right? Because the mean is 0. But variance is positive, right? Why is the variance positive? Because it is, look at here, z squared multiplied by density function of z. So everything is positive here, okay? So let me substitute this quantity. So you have here, this is expected value of x minus mu x plus y minus mu y squared. So expand the square, you get 3 terms, right? What are the 3 terms? A squared is a constant. First term is, write down the 3 terms, square of this plus square of this plus 2ab, right? So this is one term. So if you want, you don't need it. So a squared multiplied by that term. Then right? Yes. All right, so remember, expectation is a linear operation. So expectation of the sum is sum of the expectation, right? Yes. We just went through this, right? Expectation of the sum we had shown here is sum of the expectation of gixy, right? So you have 3 terms. So expectation of this is a constant goes outside. So what is the expected value of the first term? Anyone? Right. So this is going to be a squared multiplied by sigma x squared plus the second term is what? 2a is a constant. What is this term? Expected value of this. We defined it. That's the covariance of x comma y. So 2a multiplied by covariance of x comma y. And the last term?
Sigma y.
Right, sigma y squared, right? Look at this. So if you plot this quantity, this will be against A, the curve will look like what? Look at here, it's a quadratic, right? A squared. So how will the curve look like? Above this or below this? Why above? Anyone knows why the curve will go like that? Yeah, because look here, this quantity is positive, we cannot cut the x-axis. But on the other hand, this is a quadratic in A. There's two roots. What happened to the two roots? It should have cut like this. Where are the two roots? Anyone? When a quadratic cuts above the x-axis, where are the roots? Huh? Right, very good. So the roots are imaginary. What is the condition for imaginary roots? Discriminant is b squared minus 4ac is. So this is, look at this is your b, right? This is your a, this is your c. So what is the discriminant? 4 times minus, remember, you remember anything about quadratic? This is your x squared multiplied by ax squared plus this is your x squared. So imagine this as the constant of x squared. This is b squared minus 4ac, right? So minus 4, what is a? A is being sigma x squared and c is, this has to be negative, right? Hello? So 4 cancels, you get what? Covariance of xy is less than sigma x sigma y, what we wanted to prove. So we have covariance of xy is less than or equal to sigma x sigma y. If that is the case, what can you say about this quantity? Anybody? What about this quantity? What would be greater than 1? This quantity is what?
Less than 1.
So what will be the bounds on this row?
0 to 1.
Remember, covariance squared, covariance squared is less than or equal to sigma x squared, sigma y squared. Covariance could be plus or minus. So rho would be rho equal to 0 is a special case. We say x and y are uncorrelated. So when will rho equal to 0? Look here, rho equal to 0 is the same as what? If rho is 0, what else is 0 here? Anybody? Rho is equal to 0 is the same as covariance equal to 0. Covariance is what? Anybody? What is the expression for covariance? Expected value of? This is equal to 0, but that's the same as saying expected value of xy is the same as, look at here. So look, if 2 random variables are uncorrelated, it's the same as saying this is also 0, right? Expected value of xy is the same as expected value of x multiplied by expected value of y. But look here, what happens if 2 random variables are independent? Look here, if 2 random variables are independent, expected value of xy is automatically equal to this. So what happens to the covariance here? What happens to the correlation? So if 2 random variables are independent, do you see that they are uncorrelated, right? Because rho is also 0. So independence shows uncorrelated, not the other way. So I'm just going to write it there. So xy are independent. We know that expected value of xy is the same as expected value of x, expected value. That means x and y are uncorrelated. I am going to show through an example that it doesn't go this way. Two random variables may be uncorrelated, but they need not be independent.